Hello everyone, in this video we will learn all about definite integrals. To begin, let's compare and contrast indefinite from definite integral. When you say indefinite integral, it has no specific values. When you say definite integral, from the word definite, it has specific values from a until b. So basically, a and b are the limits of the integral. So writing this in notation form, we will have this, the integral of f of x dx evaluated from a until b. So the first thing to do here is solve for its indefinite integral. So next step is substitute the upper limit and the lower limit to the integral, then subtract. This is also known as the Fundamental Theorem of Calculus. So let's have an example. Evaluate the definite integral of 2x dx evaluated from 1 until 2. So graphing this one, it looks like this. This is the graph, this yellow line here. This is the graph of y equals 2x. Our limits here, we started from 1 until 2. So writing this in symbols, let's have this, the integral of 2x dx evaluated from 1 until 2. So first thing to do here is solve for its indefinite integral. So to do that, add the exponent by 1, then divide the integrand with the new exponent. So with this will become 2x squared. Our exponent is 2, so divide the integrand by 2. Then plus the constant of integration, again evaluated from 1 until 2. So at this point we can cancel 2, so we end up with this. So x squared plus c evaluated from 1 until 2. So next step is to substitute the upper and the lower limit. So this will become 2 squared plus c minus the lower limit is 1 squared then plus c. So take note at this point we can cancel c. So that's why in the process of solving for indefinite integral, need not to write the constant of integration at this part. So again, we simplify this. We will have 4 minus 1. So therefore, we have here the answer as 3. So what is the meaning of this 3? So this 3 here is actually the area of this part here. So again, we have here this one here, this is the width. So to find the area of this figure, so the area here is base times height. So take note, our base here is 1. On our height here, we have here 2 and 4. So 2 plus 4, get the middle, so divided by 2. So that becomes 6 divided by 2. So that's 3 times 1. So therefore, it's 3. So that's the concept of definite integral. So let's have another example. Evaluate the definite integral of the following. So we have here the integral of 8x dx evaluated from 1 until 2. So again, the first thing we do is solve for its indefinite integral and need not to write the constant of integration. So we have here an exponent of 1. So you add 1, it will become x squared. Then our new exponent, divide that. So take note, we can still simplify. 8 divided by 2, we can end up with 4x squared. Evaluate from 1 until 2. So next step is substitute. So this will become 4, then 2 squared minus 4, then 1 squared. So 2 squared times 4, that will become 16, then minus 4. So the answer here is 12. Okay, another example. Evaluate the integral of x cubed dx evaluated from 2 until 4. So take note, the first thing we do is solve for its indefinite integral. So add the exponent by 4 and divide by 4. So evaluate from 2 until 4. So at this point, we substitute. So this would become 4 to the power 4 over 4 minus 2 to the power 4 over 4. So this one, 4 to the power of 4 divided by 4. So that's actually 4 cubed. So that would become 64. And this one here, it's 16 divided by 4. So minus 4. So the result here is 60. Okay, another example. Evaluate the integral of the constant 5 dx evaluated from 3 until 8. So take note, the integral of 5, this would become 5x evaluated from 3 until 8. So at this point, let's substitute. So this would become 5 times 8 minus 5 times 3. So this would become 40 minus 15. So the result here is 25. So take note, that's the basic process in solving for the definite integral. Now, what happens if you are given a polynomial? So how to evaluate its definite integral? So given this, evaluate the integral of 9x squared minus 4x plus 1 dx evaluated from 1 until 2. So again, the first thing we do is solve for the indefinite integral. So this would become 9 cubed over 3 minus 4x squared over 2, and the integral of 1 is x. Then evaluate from 1 until 2. So take note, at this point, we can still simplify. This would become 3x cubed. This is 2x squared plus x from 1 until 2. Next step is substitute. So this is 2 cubed. This is 2 squared, then plus 2. Then minus, for the lower limit, we have 1 cubed, 1 squared, and 1. So simplifying further, 2 cubed, 8 times 3, that's 24. So this is minus 8 plus 2. Then minus, this would become 3 minus 2, then plus 1. So simplifying, this would result to 18, and this one here is 2. So 18 minus 2, so the result here is 16. Okay, another example. So this one, evaluate the integral of 3x cubed minus 5x squared over x dx evaluated from negative 1 until 3. So take note here, we can simplify. So with this, we can rewrite this as 3x cubed divided by x, that's 3x squared. 5x squared divided by x, that would become 5x. So that would mean the integral of 3x squared minus 5x dx evaluated from negative 1 until 3. So first step is solve for the indefinite integral. So this is 3x cubed over 3 minus 5x squared over 2 evaluated from negative 1 until 3. So take note, we can still simplify. So this would become x cubed minus 5x squared over 2. So at this point, let's substitute. So this x we replace with 3. So x squared, this would become 3 squared. Minus, our lower limit is negative 1. So negative 1 cubed and negative 1 squared. So simplifying further, this would become 27. So 3 squared, that's 9 times 5, that's 45 over 2. So negative 1 cubed is negative 1. So negative 1 squared, that's positive 1 times 5, so therefore it's 5 halves. So simplifying further here, this would become 27. This is 22.5, and this one here is 2.5. So substitute this 27 minus 22.5, that's 4.5. Negative 1 minus 2.5, it's negative 3.5. Negate that, so that will become plus 3.5. So final answer here is 8. Okay, another example. Evaluate the definite integral of 9x squared dx evaluated from 2 until 2. So take note of the upper and the lower limits. They are the same. So what will happen to its final answer? So let's solve first for its integral. So 9x squared, integrate this. This would become 9x cubed over 3, evaluating 2 until 2. So take note, we can still divide 9 and 3. So with this, we will have 3x cubed, evaluating 2 until 2. So at this point, let's substitute. So we will replace x by 2. Then we will subtract. So take note, 2 cubed, that is 8 times 3. So that would become 24 minus 24. The result here is 0. Now take note of this. If the lower and the upper limits are equal, the integral value is 0. Okay, another example. Evaluate the definite integral of 3x squared minus 2 dx evaluated from 3 until 1. So take note of this. The lower limit is greater than the upper limit. So what are we going to do with this? Take note of this one. If the lower limit is larger than the upper limit, interchange the limits and put a negative sign before the symbol of integral. So with this would become negative. The 3x squared minus 2 dx, then interchange 1 and 3. So at this point, the same process, let's solve for its indefinite integral, but don't forget the negative sign. So this would become negative 3x cubed over 3. So the integral of 2 is 2x evaluated from 1 until 3. So take note, we can still simplify this. So we will have negative 3x cubed minus 2x evaluated from 1 until 3. So at this point, let us substitute. So this x will be replaced by 3 as the upper limit, then minus, then x again will be replaced by 1 as our lower limit. So take note of this. So 3 cubed, that's 27, times 3, that's 81. So 2 times 3, that's 6. So at this point, 1 cubed times 3, that's 3. Then 2 times 1, it's 2. So simplifying further, 81 minus 6 is 75. Then 3 minus 2, it's 1. So 75 minus 1 and negative outside. So the result here is negative 74. So take note of this. Okay, another example. Evaluate the integral of e3x dx evaluated from 0 until 1/3. So take note, the integral of e3x is e3x over 3, then evaluated from 0 until 1/3. So at this point, let's substitute x by the limits. So we have here upper limit as 1/3, then for the lower limit, it's 0. So at this point, so 3 to the power of 1/3, that's actually 1. So this is e to the power over 3 minus, so take note, e to the power of 0, that's basically 1, then over 3. So we have here e over 3 minus 1/3. Okay, or making use of your calculators, the final answer here is 0.57. Another example. Evaluate the integral of cosine x dx evaluated from pi over 6 until pi over 3. So take note, pi over 6, this is basically 30 degrees. So from 30 degrees to 60 degree angle. So again, solve for the indefinite integral for cosine. So the integral of cosine is sine x, evaluating pi over 6 until pi over 3. So at this point, let's substitute. So we have here sine pi over 3 minus sine pi over 6. So take note, sine pi over 3, that's square root of 3 over 2, and sine pi over 6, or this is 1/2. So we will get this, or we can combine as square root of 3 minus 1 over 2. Or making use of your calculators, that is approximately 0.366. Okay, another example. Evaluate the integral of sine 2x dx evaluated from 0 until pi over 4. So with this, the integral of sine 2x, that's negative cosine 2x over 2. So evaluated from 0 until pi over 4. So at this point, this will become, so at this point we will substitute. So our x will be replaced by pi over 4, and here it's 0. So this would become cosine of pi over 2, or that is 90. So negative cosine 90, that's actually 0, then over 2. Then 2 times 0, that's 0. So negative cosine 0, that is actually 1. So positive, negative 1, so times negative, so therefore it's plus 1 here. So the final answer here is 1/2. So let's have this, definite integral using substitution rule. So take note, we can make use of the substitution rule if the given integrand consists of a function and its derivative. So for example, evaluate the definite integral of 4x plus 1 cubed 4 dx evaluated from 0 until 2. So to do this, let's substitute. So let u be equal to 4x plus 1. So take note, the derivative of u is du. The derivative of 4x is 4 dx, and the derivative of 1 is 0. So at this point, let's substitute. So this 4x plus 1 cube, we will rewrite this as u cube. And this 4 dx, we will replace that with du. So that would mean the integral of u cube du evaluated from 0 until 2. So take note, the indefinite integral of u cube, that's actually u to the power 4 over 4, evaluated from 0 until 2. So at this point, we will replace u again with 4x plus 1. Then raised to the power 4 over 4. So at this point, let's substitute with our limits. So our x here will be replaced by 2. For the lower limit, our x here will be replaced by 0. So with this would become 4 times 2. That's 8 plus 1, so that would become 9 to the power 4. So 4 times 0, that's 0 plus 1, so that's 1 to the power 4. 9 to the power 4, that's 6,561. Minus 1 over 4, so that's 6,560 over 4. Divide this. The final answer is 1,640. Okay, another example. Evaluate the integral of x squared times x cubed plus 5 squared dx evaluated from 0 until 1. So the same process, let's assign u as x cubed plus 5. So again, derivative of u is du, derivative of x cubed is 3x squared dx, and the derivative of 5 is 0. So take note, the given here is only x squared dx. So we need to eliminate the 3 by dividing both sides by 3. So with this, we will end up with du over 3 x squared dx. So at this point, let's substitute. So this x cubed plus 5 will be replaced with u squared. Then x squared dx will be replaced with du over 3. So this would become the integral of u squared du over 3 evaluated from 0 to the power of 1. So at this point, let's find its integral. So take note, du over 3, that's the same as 1/3. So place that at the start. So the integral of u squared, that's u cubed over 3 evaluated from 0 until 1. So simplify further, this would become u to the power of 3 over 9 evaluated from 0 until 1. So at this point, we will replace u with the original given as x cubed plus 5, then cube over 9 evaluated from 0 until 1. So at this point, replace x with the upper and the lower limit. So for the upper limit, that's 1. For the lower limit, it's 0. So with this would become 6 cubed over 9. So this is 5 cubed over 9. So simplifying further, this is 216 over 9 minus 125 over 9, or that is basically 91 over 9. Riemann sums, left and right endpoints, and the midpoint rule. In mathematics, a Riemann sum is a certain kind of approximation of an integral by a finite sum. It is named after the 19th century German mathematician Bernhard Riemann. One very common application is approximating the area of functions or lines on a graph, but also the length of curves and other approximations. So let's have an example. Approximate the area under the curve y is equal to x squared from 0 until 8. So let's start with the left Riemann sums, or it's the left endpoints. So let's graph y equals x squared. So this red graph here, that's y equals x squared. So from 0 until 8. So let's decide as to the number of squares. Now suppose if we will have 4 rectangles, so we will divide this into 4. So let's draw our rectangle. So take note, it should start from the left endpoint. So from the left endpoint, so that would simply be a line. So for the second endpoint, so this one is a rectangle. So take note, one side should touch the curve. So for the third rectangle, or the next rectangle, so this will be the rectangle, and the last is this one. So take note, with the left endpoints, the left part of the rectangle should touch the curve. So for a left endpoints, take note, there are parts here that are not shaded. So when you say left endpoints, it's actually an under approximation of the area. Okay, now when you say finding the area of a rectangle, is basically it should be length times width. So for the width here, that would be from one endpoint to another endpoint. So that would simply be the change in x. While the height, so we have here different height of the rectangle, in which it is defined as the function of x squared. So take note, our limit started from 0 until 8. So to find the width or the change in x, that would be the end limit minus the starting limit divided by the number of squares. So that would be 8 minus 0 divided by 4. So therefore, we will have our interval as 2. So from 0, we will have 2, 4, 6, and 8. So take note of this one. So again, if we have here 2, so substitute x squared, we'll get 4. If we will have 4 here, let's 4 squared, that would become 16. If we have 6 here, then squared, so therefore that would become 36. And take note, we started from 0, so therefore 0 squared, it's 0. So at this point, 4 times our height is 4 and the width is 2, so 4 times 2 you'll get 8. 16 times 2, that would be 32, and 36 times 2, that would be 72. And 2 times 0, that's definitely 0. So you add all of this, 8 plus 32 plus 72, the result here is 112. So using the left end point method, so the area of the curve under this curve is 112 units. So that's the concept of Riemann sums. Now, how about doing it mathematically? So with this, we will have the area, making use of the left end points, is the summation of the change in x, which is the width, times the height evaluated from 1 until 4, or with your I started from 1 until 4. So take note, this is left. So our width here, we have here as 2. So left endpoints, we start from 0. So that would be 0 squared, f of 0, 2, 4, and 6. So 0 squared, that's 0. 2 squared, that's 4. 4 squared, 16. And 6 squared, that's 36. So add all of this. So that would become 56. 2 times 56, that's 112. So that's how are you going to do it. Okay, another. Now, let's make use of the right endpoints. So, how to do it? So, again, sketch the curve, x squared. So, take note at this point, this is already right. So, with this, the right side should touch the curve. So, our first graph is this. So, we'll start from 8. So, the right side will touch the curve. For the second rectangle, so we will have this for the third rectangle, and of course, we will have the fourth rectangle. So this is right end point. So the same thing, our width here is 2, and our height here is still x squared. So that would be the summation of the change of x, f of x squared, where I started from 1 until 4. So area of the right end points. So again, our width is 2. So we will have f of 2, f of 4, f of 6, and f of 8. So with this would become 2. So 2 squared, that's 4. 4 squared is 16. 6 squared is 32. And 8 squared is equal to 64. Adding all of this, we will have 120. So times 2, it's 240. So making use of the right Riemann sums, the result is 240. But making use of the left endpoints, the result is 112. So observe this one. For the right endpoints, take note there are extra parts here. So it means that making use of the right endpoints, that is an over approximation of the area under the curve. Unlike with the endpoints that there are parts not included in the rectangle. Left endpoints is under approximation, while right endpoints is over approximation. So to reconcile that, we will find its average. So area here would be area of the left plus area of the right endpoints divided by 2. So 112 plus 240 divided by 2, so that would be 176. So that's the approximation. Okay, next. Now, again, the area making use of the average of the left and the right is 176. What if I will ask, what is exactly the area of the curve? So with that, we can make use of the definite integral. So that would be the integral of f of x dx evaluated from a until b. So let's substitute. So take note, our function is x squared dx evaluated from 0 until 8. So step 1, evaluate the indefinite integral. So that's x cubed over 3 evaluated from 0 until 8. So at this point, you substitute. So this would become 8 cubed upper limit and 0 cubed for the lower limit. So with this would become 512 divided by 3. So the result here is 170.67 square units. So take note of that. Okay, now what happens if the number of rectangles is increased? Like the same given, y equals x squared, evaluated from 0 until 8. So at this point, from the rectangles of 4, we will change it to 8. So again, from 0 to 8, so the width is b minus a over n. So 8 minus 0 divided by 8. So the result here is 1. So making use of the number line, so we will have 8 divisions here. So that would have an interval of 1. So making use of the left endpoints, so that would be the summation of the change of x times f of x squared from 1 until 8. So take note of this, our width is 1. So we'll start from the left endpoint. So that would be 0, 1, 2, 3, 4, 5, 6 until 7. So square that. So 0 squared is 0, 1 squared is 1, until 7 squared is 49. So adding all of this, so left area of the left endpoints, making use of left endpoints is 140. Now, what about making use of the right Riemann sum? So, again, the same thing. So, that's the summation of width times f of x squared evaluated with I from 1 until 8. So, if we will start from the right, so that would mean from 1 until 8 or 8 until 1. So, that's the right side way of identifying the right endpoints. So the same thing, so 8 squared is 64 until 1 squared, which is 1. So adding all of this, so for the area making use of the right Riemann sums, it's 204. So take note, this is over approximation and this is under approximation. So get the average. So that's 140 plus 204 divided by 2. That's 172. Now let's compare and contrast. So take note, if the number of squares is 4, left is 112, right is 240, average is 176, the actual area is 170.67. If the number of squares is increased to 8, the left is 140, the right is lowered to 204, and the average is lowered to 172. So take note of this. As the number of rectangles increases, making use of Riemann sums approximation, its value is getting nearer and nearer to the actual value. So take note of that. Okay, now another method of using Riemann sums, or another method, is the midpoint rule or the midpoint Riemann sum. So how to do this? So making use of the midpoint rule, so still if our n is 4, so the same process, so 8 minus 0 divided by 4. So our interval here is 2. So sketching the curve y equals x squared. So with this, from 0 until 8, let's identify the midpoint. So our midpoint here, this is 1, this is 3, this is 5, and this is 7. Then let's sketch our rectangle. So this is the first rectangle, this is the second, this is the third, and of course, this is the fourth. Okay, so let's solve for the midpoint rule. So that's width times the height evaluated with I from 1 until 4. So with this, we'll start from our first midpoint, which is 1, then 3, 5, and 7. So take note, 1 squared is 1, 3 squared is 9, 5 squared is 25, and 7 squared is 49. So simplifying this, we will have 168. Now let's try to compare and contrast. So again, the same number of rectangles. Making use of the left Riemann sums, that's 112. Right Riemann sum method, that's 240. And the midpoint rule is 168. And the actual area is 170.67. So take note of the 3 methods of Riemann sums. It is the midpoint rule that is closest to the actual area. So take note of that. Okay, let's have another example. Approximate the area of the curve. Y is equal to x cubed from 0 until 10 with n is equal to 5, or the number of squares is n to 5. So 0 to 10, so solve for the width. So that would be 10 minus 0 divided by 5. So our interval here is 2. So sketching this interval in the number line. So we start from 0, 2, 4, 6, 8 until 10. So making use of the left endpoints. So that would be the summation of the change of x times f of x cubed from 1 until 5. So take note from the left. So you have here 0, 2, 4, 6 until 8. So 0 cube is 0, 2 cube is 8, 4 cube is 64 until 8 cube, which is 512. So with this, add all of this. So this would total 800 times 2. So making use of the left endpoints is 1600. So take note, this is under approximation. Now making use of the right endpoints. So at this point, we will start from 10 until 2. So the same process. So we have here 2 or with, then 2 cube, then 4, 6, 8 until 10. So take note, 2 cube is 8, 4 cube is 64, and 10 cube, that is 1000. So simplifying further, so this would become 1008 times 2, that's 3600. So take note, 3600 is an over approximation. So let's make use of the midpoint rule. So take note, the midpoint of 0 and 2, so that would become 1. This is 3, 5, 7, and 9. So substitute here. So 1 cube is 1, 3 cube 27, until 9 cube, which is 721. 29. So add all of this. That's 1225 times 2, so it's 240. Now, what about the actual area under the curve? So again, making use of the definite integral. So that's the integral of x cubed dx evaluated from 0 until 10. So solve for the integral. So x4 over 4 evaluated from 0 until 10. So substitute. So 10 to the power 4 over 4 minus 0.4 over 4. So simplifying, this would become 10,000 over 4, or that's approximately 2,500 square units. So take note of this 3. It's the midpoint rule that's closest to the actual area. Area between curves. So how to find the areas of plane regions using definite integral. So if we're given this, wherein the lower part is along the x-axis, and this is the graph of y equals f of x, or the function. So to find the area, that's the definite integral of f of x dx evaluated from a until b. Now it's different if the curve or the plane is between two curves. Like we have here the upper curve as h of x and the lower curve as g of x. So to find the area here, that would be the integral of the upper curve, which is h of x, minus the lower curve, which is g of x dx evaluated from a until b. Now, if the curve is like this, so if one of the side is along the y-axis, so to find the area here, that would be the area of, or the integral of g of y dy evaluated from c until d. Now if the curve is defined by two functions from the left to the right, so from c until d, so to find the area here, that would be the right curve, which is f of y, minus the left curve, which is g of y dy evaluated from c until d. So take note of that. Okay, let's have an example. Find the area of the plane region bounded by y is equal to 8 minus 2x, the x-axis and the y-axis. So with this, we need to sketch first 8 minus 2x. So doing this, we can make use of this. So we have here, if our x is 0, so substitute, this would become 8. And if our y is 0, so our x here would become 4. So sketching this in the Cartesian plane, we will get this. So we have 8 and 4, so connect it with a line, so since it's linear. Then we have here the x-axis, and we have here the y-axis. So what's the area of this region? So take note, this is a right triangle. So to do that, that would mean base times height divided by 2. So our base here is 4 and our height is 2. So simplifying, the area here is 16 square units. Now, how to do this making use of the definite integral? So that would mean the definite integral of 8 minus 2x dx evaluated from 0 until 4. So with this, find the integral. So that's 8x minus 2x squared over 2. So you can still simplify. So we can cancel 2. So at this point, let's substitute. upper and lower limits. So we have 4 and 0. So with this is 32 and this is 16. So 32 minus 16. So still it is 16 square units. Okay, another example. Find the area of the plane region bounded by 3x plus 1, x equals 1, x equals 3, and the x-axis. So again, you have to sketch the linear graph, which is 3x plus 1. So take note, our y-intercept here is 1. So our slope is 3. So that would mean 1, 2, 3, then run by 1, 1, 2, 3, then run by 1, 1, 2, 3, run by 1, and so on. So this is the graph of 3x plus 1. We have here the x-axis, so that's our lower limit. And we have here x equals 1, and we have here x equals 3. So what's the area of the shaded part? So making use of the definite integral, so that would be the integral of 3x plus 1 evaluated from 1 until 3. So take note, the lower part here is the x-axis. So this would become 3x squared over 2 plus x evaluated from 1 until 3. So substitute the upper and the lower limits. So upper is 3 and the lower limits is 1. So simplifying, this is 27 over 2 plus 3. And this would become 3 halves plus 1. So this would become 16.5 minus 2.5. So final answer here is 14 square units. Okay, another. Find the area of the plane region bounded by the curves y is equal to x squared minus 2 and y equals x. So take note, we have two curves here. So this is the graph for x squared minus 2. So it is parabolic, it opens upward. So take note, we have a constant minus 2. So we have to lower our vertex at negative 2. Then y equals x, this is a linear. So if our x is 0, our y is 0. If our x is 1, our y is also 1, and so on. So we will have this graph. And take note, their point of intersection is at negative 1 until positive 2. So therefore, what's the area of this curve, of this region bounded by the two curves? So take note, our upper function is f of x equals x or y equals x. Our lower function or our lower curve is defined as x squared minus 2. So with this would become the integral of f of x minus g of x dx. So meaning it is upper curve minus lower curve. So let's substitute. So our upper curve is x, our lower curve is minus x squared minus 2 dx evaluated from negative 1 until positive 2. So simplify this, get its integral. The integral of x is x squared over 2. So the integral of negative x squared, that's x cubed over 3. So take note, it's negative of negative. So that would become plus 2. So the integral of a constant is 2x evaluated from negative 1 until 2. So at this point, let's substitute. Upper limit is 2 and the lower limit is negative 1. So simplifying this, we will get this one. So 2, this is 4 over 2, that's 2. So 8 over 3, then plus 4. So minus, this is 1/2. This is negative 3. So times negative, so that's plus 1/3. Then minus 2. So simplifying further, we will have 10/3 plus 7/6, or that's approximately 9 over 2 square units, or that's 4.5 square units. Okay, another. Find the area of a plane region bounded by the curves y is equal to x squared and x is equal to y squared. So take note, we have to graph this. So y equals x squared. So it's a parabolic that opens upward. So we have this. So, and x equals y squared. So it is still a parabolic graph that opens at the right. So take note, the intersection or the bounded curves, the plane region is this one. So take note, the lower curve is y equals x squared. Well, the upper curve, this one here is x is equal to y squared, or basically y is equal to square root of x. So take note of this, how to find the area of this one. So expanding this is actually the graph. So this is y is equal to square root of x, this blue part, and the red part is y is equal to x squared. So getting its area. So that would be upper curve minus lower curve. So take note, our upper curve is square root of x and our lower curve is x squared. Then our intersection is at 0 and at positive 1. So at this point, let's get its integral. So this is x to the power of 1/2. So plus 1/2. So that would become 3/2 divided by 3/2. So this would become x cubed over 3 evaluated from 0 until 1. So simplifying this would become 2x to the power of 3/2 over 3 plus x cubed over 3 from 0 until 1. So let's substitute our upper and lower limits. So upper limit is 1, lower limit is 0. So at this point, this would become 2/3 plus 1/3. So 2/3 plus 1/3, so that's 3 over 3. So therefore, it's basically 1 square unit. Okay, another. Find the area of the plane region bounded by the curves y is equal to x squared and y is equal to -1 from x -1 until x equals 2. So graphing this is the graph for y equals x squared. Then y equals -1. So this is our lower limit. Then we start from -1 until positive 2. So what's the area of this region? So take note, our upper graph or our upper curve is x squared and our lower curve is -1. So again, finding its area, so that would be upper minus lower. So our upper curve is x squared, our lower curve is -1. So starting from -1 until positive 2. So take note, negative of negative, so that's plus 1. So getting its integral, so x cubed over 3, the integral of 1 is x, evaluated from -1 until 2. So at this point, let's substitute. Our x is 2, upper limit, our lower limit is -1. So simplifying, this is 8/3 plus 2, this is -1/3 minus 1. So simplifying, this would become 14/3, and this one, this would become 4/3, so it's 18 over 3. Simplifying, this is actually 6 square units. Okay, another example. Find the area of the plane region bounded by the curves y is equal to x squared minus 4x and the x-axis. So take note, this is the graph for x squared minus 4x. This is the graph of the x-axis. So take note, our upper limit is 0, or our upper curve is 0. Our lower curve is x squared minus 4x. So what's the area of this region? So again, substitute at this point. So our upper function, our graph is 0. Our lower function is x squared minus 4x dx. Evaluated from 0 until 4. It's because these are their points of intersection. So simplifying this is -x squared and plus 4x. Get its integral. So it's -x cubed over 3 plus 4x squared over 2. You can still simplify this as 2x squared, evaluated from 0 until 4. So substitute our upper limits and our lower limits. So this would become -64 over 3 plus 32. Then, of course, this is 0. So simplifying, this is -64 over 3 plus 96 over 3. Or this is 32 over 3, or approximately 10.67 square units. Okay, another example. Find the area between the graph y equals -x cubed and the x-axis from -2 until positive 2. So take note, graphing -x cubed, it looks like this. So starting from -2 until positive 2. So take note, you have two sets of functions here. So to do this, we will have multiple functions. So find the area of this curve and find the area of this curve, then add. Okay, so to do that, let's have this. So we will start here from -2 until 0. So our function here is -x cubed. That's our upper function. Our lower function here is 0. So that would become -x cubed from -2 until 0. So get its integral. So -x4 over 4. Then substitute. Our upper limit is 0 and our lower limit is -2. So simplifying this, cancel. So negative 2 to the power of 4, that's 16. So times negative, so 16 over 4, that's 4 square units. So the area here is 4. Now, for the second function, so take note, our upper function here is 0, and our lower function here is negative x cubed. So this is the function. So simplifying this would become the integral of x cubed dx evaluated from 0 until positive 2. So get its integral, x4 over 4, evaluated from 0 to 2. So substitute, upper limit is 2, lower limit is 0. So still, this is 16 over 4, or this is 4. So adding the area of the two regions, so that's 4 plus 4, or that is 8 square units.